Okay, we now continue with types of functions, rejections, injections, adjections, and so on. Okay, so let's and this function. Right. We say that f is injective if for all I will write it for all x, for all a and b x, if f of a equals f of b, then what? Then a equals b. Usually people state it in contraposition. You know what contraposition is? When you have implication and you swap the sides and put negation. Okay, so in contraposition, I don't know why people do it in contraposition with negation, so you don't need negation. It's written as follows. For all a x, so this becomes inequality, and it becomes equality. Yeah, maybe it's more natural to say different values go to different outputs, but this is the positive way of saying it. If the values are equal, then the inputs are equal. If the values are equal, then the inputs are equal. Some examples. Okay. So this will be questions. So which of the functions are injective, which are not. So first, yeah, because it says by definition it says if it's when applied to A, say when applied to B, so we have A equals B, then B equals B, which is okay. F R R F F R R F of X is X squared. Is this injective? X squared. Is this injective? Why?
The square of the negative.
Yeah, not injective. Yeah. For example, f of, because f of minus a is f of a. But if you even we can include a zero as well. If you restrict positive numbers, now it's injective. So the domain matters. If we have the same formula but the domains are different, and the result will be different. Um, let's now talk about the x, y. We say that
For every element in Y. That exists. So it's not that.
yeah. Okay, I forgot some diagram, for example, if we have set here and set here, it doesn't matter how many elements here we have on the right, but the elements don't have the same output in injections. And in surjections, we have that if usually the side the set on the right here has no more than the side on the left. So the set on the right here has no more than the side on the left. So if we have 3 points here, and maybe okay, 4 points here. We can have here, 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 and what should we do? So this is surjection. Everything on the right has a so-called cleavage. Okay. Read some examples. Okay. Identity. Is it subjective? Yes. Why? Why subjective? So here we have identity. When does identity of x equals y? No, so if y, if x is in x, then what's the pre-image of x? So we have from x to x, and we take some element x here. What is pre-image? The same x here. That's pre-image. Identity of x. This is then okay. I have a because it's not there. Identity of a equals a. We say that a is pre-image. Okay, in this case. So identity is always injective and surjective. Let me leave f from R to R, f of x equals x squared, f of x equals x squared. Is it subjective?
No,
Why?
because it doesn't map to any of the negative units.
Yeah. So when you want to show that something is subjective, you need to solve the problem for any element to the right set we want to solve the problem, find x so that f of x equals y. Because the problem f of x equals -1, we don't have solutions. So -1 doesn't have pre-images. I think this is clear. What it is. Real numbers that are bigger in 0 or more. So, set of all your numbers, that x is equal to, and then f of x is x squared. What about that? X is that. Surjective. Cos n y r f of plus minus s is 1 y is 1. So this is a image. It's very important. Okay, what about that? No, it's not well defined. Yeah, this thing doesn't exist. I cannot ask the question, is it surjective or not, because this is not a valid function. So f is not well defined. So surjectivity or injectivity. This nonsensical question. Well formed. Now, let me prove some very interesting proposition. How subjectivity and injectivity connect. First definition. I can do without this definition, but I will say those words often, so I will find them. Let f is from x to y, x and y sets. F is function from x to y, and z is function from y x. So these are the opposite directions. If the function of g and f is the identity of x, we say that. Do you know how we say? Yeah, but what kind of events? So G is a left inverse of f. It's a left inverse G and of yeah. It's not even definition, it's some equation. And F is a right inverse. Of G. Okay. If it's okay, if these are, if you have both directions, we say that they're just a button for this is just some human language, if you see, to know what it means. So we can now have very interesting demonstration. I will not prove it because it's as an exercise. I will not prove it because it's as an exercise because it's easy to prove. Okay, we have sets. F is function from x to y, and there is function from y to x, and g controls f is identity. Then F is injective, and G is surjective. In fact, the opposite is true in some sense. If F is injective, there exists left inverse, and if you sum the maximum of choice, which I don't think true, but most people are, then if G is surjective, there exists F subjective. The opposite part. I will show you just a moment why this is important, but let me give some diagram. For example, we have the elements here. 4 elements here. This is x, this is y. So and 0, 1, this is y. And J. And it's again C. It doesn't matter. See. And in this diagram, you see that the function f is injective, and all the values map to different elements. And g is surjective, x. Right? Now comes something very interesting. Injections and surjections can have interpretation as bundles, which are usually bundles in geometry have more structure, but even without structure, we can have very interesting interpretations. So bundles and sections interpreted so from the room subject somewhere, but I cannot decide the opposite side. And the triple and E is a bundle over M. Now, surjections, they expect to have like they expect to have items. Items so sum up x from N to E, sum up x from N to E. So P position x equals identity of N. And for element x in M, so a point in the manifold usually, the set, so-called, I'll go about the image now, let's write it rigorous. Set Ex, which is defined by the image of X. The image is all the points that map to X. So this is the point, all the points E such that P of E equals X. Is called how is called EX. The fiber is called the fiber of X. And we have the decomposition disjoint union. Disjoint, so all the sets will be different. What was the decomposition? The decomposition of A. So this is the disjoint union of P of X. This sign means union but says do not intersect. So it's union but says do not intersect. So all the sets don't have common elements. So this is bundle decomposed into fibers. Well, what's the bundle? A triple or what? Well, okay, let me give an example.
So is there a difference for the direction of X?
Well, it's the union of fibers is the whole bundle. But I'm not sure.
I put sheet.
Yeah, but I've got the sheet as well, but I'm not sure, so let me just keep that.
Keep it. The right inverse is the right inverse X M to E. Would you call it? Would that be a section of M or a section of
Section No, section of the bundle. Section of the bundle. Okay, now let me give example because this is very extended. And the tangent bundle is one example, but it's not very good, so I will give very so let L0 and L1 are real numbers, positive, and L1 is bigger than R0. Define the annulus. Okay. Consider the so-called annulus. So annulus is something here. So this is the set between two circles. So the annulus is defined E real number, all pairs of real numbers, such that uh, R0 squared. I will consider the closed one. It doesn't matter if it's not open for our example. X squared plus y squared smaller than L1 squared. Now, M is the integral L1 L0 to L1. Can you tell me how to project point in this annulus to this interval? Yeah. Here, xy is the square root of x squared plus y squared. Is the radius of this the distance to the origin. Is it surjective? Yes, because if R is okay, what let us find the the fibers. Here xy is a set of points, so it's the same. But, no, sorry. Here, let's R belongs to this interval, R0 to R1. And we want to find a fiber. So the fiber is a subset of X corresponding to point of M. So E of R, by definition, is the set of all X and Y, R squared, such that the projection is equal to R. What's this? A circle. So this is the circle. So this is the set of points A, cosine theta, and sin theta, theta is from 0 to pi. Okay. So this tools can be decomposed into fibers. So this fiber, this fiber, this fiber, and so on. And can you suggest a section? So a section is a function, so it's a right inverse to the projection. So we have to start with our radius, go to a point, and get to the same number. So, okay, it's called section because it's actually a cross section. It's a cross section. So any cross section, like a line, something like that, also are all arrays starting from some point exactly ER0 to ER1. For instance, X of R will be some R cosine. I don't know, maybe P over 4. Doesn't matter, the angle doesn't matter. Every angle works. So we start with point here, map to a point on the annulus, and then the distance to the, when we take the projection is the square root of the squares here, and it's R. In fact, I can put cosine of any function here and sine of any function here. And these are the sections of this bundle. So this terminology, sections, bundles, is used in differential geometry, and this is the where it originates from. We have some bigger set, and the smaller set, the smaller space can subdivide it into fibers. And we can take a cross section, which is a map from the smaller to the bigger one. Let me finish with directions and give some. So what we did so far was very basic set theory like that, and this is something that it's not found in set theory books because it's not used there, but we will talk about bundles, and I wanted to show that the idea is very simple. It doesn't need very anything complex. We say that F is bijective when F is bijective. Yeah. Right. This inverted considered. Um, and the most important thing about bijections is that they give inversible maps. So we have the following proposition. If inversible maps. So we have the following proposition. F is bijective when it is invertible. Which means that it has both a right and a left. Oh, it's not proposition, it's proposition. No, not proposition. I.e., there exists a shift from y to x such that the composition of g of f is the identity of x, and exists h of y to x such that I don't know why I write such that I don't h of composition of f is sorry. I bring here y. Something that can be said is that these functions are unique and they are equal, g and h. So moreover, g and h are unique. It's not very precise how I state it. I suppose it's unique. And g equals h. So a bijection has inverse and it's unique. So we have that f opposed to g is identity of y and g equals to f is identity of x. This is what the bijective functions have. Uh, okay, so I have to say maybe trivial things for bijective. So it's to prove, and we don't have much time, so I may go give some assignments for anybody to yeah, to exercise. Okay, let me see some problems. So prove that f is injective whenever we can prove one of the directions is not necessarily preferably. F is injective whenever it has left inverse. F has right inverse. Then F is surjective. For this three, you have to, if you do this only if you are interested, because it requires an axiom of choice. The proof is simple, but it uses some very strong argument. So it's the opposite direction. F is surjective, then F has left right hands. Or if the proposition I just stated. Now, if you combine all this proposition, you will get for free that F is bijective whenever it's invertible. Because for injectivity is equivalent to left inverses, and surjectivity with axiom of choice is equivalent to right inverses. But bijectivity is equivalent to invertibility without the axiom of choice. With invertibility without the axiom of choice. So if it's bijective, you can prove it. So this is injective, it means it has a left inverse, but you can prove that it has a left inverse without the axiom of choice. So F is bijective whenever F is invertible. Okay. Now the uniqueness of inversion and so on, I will talk about this next time when I talk about groups. Oh, yes. 5. Prove that the decomposition, the decomposition of fibers that was before E. Ex is different than y, then Ex intersection with y is an empty set. That means that it's a disjoint union. Okay, I think these are enough problems. And let me finish the stream. Other questions that you want to ask for everybody to the live stream? Yes. I sent the link to Peter, and he told me he couldn't participate today, but maybe some of his students. Yeah. Okay, I'll finish the live stream.